Okay, welcome to the final lecture of the course. This final lecture will be on using truth tables to assess sentences and arguments of sentential logic, right? So remember last week we learned how to translate language or ordinary language statements to propositional logic. So that's something that we learned last week. So for example, and we saw that just like when you're translating from let's say one language to another, from English to French or English to German or wherever it may be, or German to English or French to German, whatever the languages you're translating, there are often idiomatic expressions that you need to uh, talk about in order to effect accurate translations, right? And so idiomatic expressions then are expressions that may be peculiar to one language but are difficult to translate into another. So what I did last week is I went over a number of idiomatic expressions and how to translate them into sentential logic, into propositional logic. So an example is let's say it rains only if it snows. In that case, that's going to be R, then S, right? So if it's only if, you keep the order the same, R, then S. If R, if S, then that's going to be S, then R, right? So the order changes. If you have if and only if, P, if and only if Q, that's P double bar, triple bar Q, right? If you have neither P nor Q, there are two ways you can translate that: tilde, parentheses, P or Q, parentheses, or you can translate it equally plausibly as not Q and not P. That's because of something called De Morgan's law, all right? In addition, if I say not both P and Q, that will be tilde, parentheses, P and Q, parentheses, or you can translate it as not P, wedge, not Q. And that again is by De Morgan's laws, okay? Um, Also P but Q, P although Q is just translated as P and Q. P unless Q is translated as P or Q. And so basically what you can do is you can take a language, you can take an ordinary language sentence and translate it into propositional logic, all right? And so that's what we focused on last week. And the exercises that you handed in at the lab, they were focused on translating from natural language into propositional logic, okay? So this week, we're going to switch gears a little bit. Now that we've learned how to translate from natural language to propositional logic, now we're going to learn what is called the semantics, the meaning of the connectives. And then using that semantics, we will be able to assess whether a statement is contingent, contradictory, or tautologous, and we'll be able to assess whether an argument is valid or invalid. So if you look at this first slide, what I have here is called a truth table. This is called the characteristic truth table for the 5 truth functional connectives. So remember from last week, there are 5 truth functional connectives. There's negation, not P. There's conjunction, P or Q, or sorry, P and Q, apologies. There is disjunction, P wedge Q, all right? And remember from last week that the disjunction in propositional logic is inclusive and not exclusive. P then Q is just P horseshoe or whatever you want, arrow or whatever convention you want to use Q, and then P double bar, or sometimes people translate it as triple bar Q, is P if and only if Q. So the 5 connectives then are tilde, not, ampersand, conjunction, wedge, or, inclusive or, horseshoe, if then, which is sometimes known as the material conditional, and the double or triple bar, P if and only if Q, that's if and only if, all right? And so you can render what those connectives mean by drawing what is called a truth table, all right? Basically, what the truth table does is it tells you what each connective means. By the way, another point that I made last week is that tilde is a unary connective, whereas the other connectives are binary, right? So tilde is just takes one expression and makes it into a complex expression. The other 4 connectives are binary. They take 2 expressions and they make them into a more complex expression. We also said last week that the connectives in propositional logic are truth functional, okay? That means that the truth value of the entire statement is purely a function of the truth value of the components, right? We saw that other connectives are not truth functional, like because, necessary, since, a lot of temporal connectives, they're not truth functional, right? Because you can know the truth function, or you can know the truth value of the components and still not necessarily know the truth value of the entire statement. So what sentential logic or propositional logic focuses on are what are called truth functional connectives, all right, where the truth value of the entire statement is a truth function of the component statements. So looking at this table, then we see that the meaning of not P is as follows: that whenever P is true, not P is false, right? And whenever not P is false, then not P is true. Okay. For P and Q, that means taking P and Q together, both P and Q. Clearly, it's true when both are true. But if either one is false or both are false, then P and Q is false. And so that's this column here in the truth table, right? Now we go to P wedge Q. Well, because the OR is inclusive in propositional logic, then P and Q can both be true, and P or Q will still be true. Obviously, if one of them is true, then P or Q is true. But if both are false, then clearly P or Q is false. If I'm saying it rains or it snows, but it doesn't do either, then it's false that it rains or snows, right? Okay, P then Q. The only time when P then Q is false is when P is true and Q is false. If I say if P then Q, and you tell me that, well, P is true and Q is false, then that tells me that P then Q is false. Otherwise, P then Q is true. And finally, for P, if and only if Q, if P and Q have the same truth values, it's true. So look at the first row and the fourth row. P, if and only if Q, is true when both have the same truth values, either when both are true or both are false. If they differ in truth values, then P, if and only if Q, will be false. All right. And so this table gives you the complete semantics for the connectives of propositional logic. And it can be summarized as follows: not P is true if and only if P is false. P and Q is true if and only if P, Q are both true. P or Q is false if and only if P, Q are both false. Otherwise, it's true. P then Q is false if and only if P is true and Q is false. Otherwise, it's true. P if and only if Q is true, if and only if P and Q have the same truth value. And so this table tells us what the connectives mean. Using this basic truth table, we can calculate the truth values of complex statements involving parentheses and brackets. And we can also, using this table, so we can use this to determine the truth values of those statements and to tell whether they're contradictory, contingent, or tautologous, and I'll define those terms in a minute. And we can also use these basic truth tables to discern whether an argument is valid or invalid. Okay, so this truth table is very important. So as I say in the next slide, we can construct truth tables for complex sentences of propositional logic to determine their status. The number of rows depends on how many types of atomic sentences the proposition contains. To determine how many rows the truth table we have, we use the simple formula 2 to the n, where n is the number of atoms. So consider not A or B, we have two atoms, A and B. So then we have 2 to the 2, or a 4-row table. A or B or C, as you can see, has 3 atoms. So then its truth table will have 2 to the 3, or 8 rows. We see that A or B and C or D has a 16-row table. Why? Because you have 4 atoms, A, B, C, and D, and 2 to the 4 is 16. So the number of rows of the truth table for a complex sentence depends on the number of atomic expressions it contains. An atomic expression is any expression that itself doesn't contain any connectives, any truth functional connectives, right? So each row of the truth table represents an assignment of truth values to the atoms. So let's go back to our basic truth table again. What this table tells me is that the truth values of the complex sentences are a function of the truth values of the component sentences, right? And so it tells me what happens when the truth values vary for each sentence. Each of these rows is sometimes known as a possible world or a truth value assignment. There is a truth value assignment or world where P and Q are both true. In that case, not P is false, P and Q is true, P or Q is true, P then Q is true, P if and only if Q is true. There is a possible world or truth value assignment where P is true and Q is false. In that case, not P is false, P and Q is false because one of them is false, P or Q is true because you just need one of them to be true for it to be true, P then Q is false. That's the only time that P then Q is false is when P is true and Q is false, and P if and only if Q is false. If you have a possible world or truth value assignment where P is false and Q is true, then not P is true. It takes on the opposite truth value of P. P and Q is false because one of them is false. P or Q is true because one of them is true. P then Q is true. P if and only if is Q is false because they differ in truth values. Finally, if both P and Q are false at that truth value assignment or possible world, then not P will be true. P and Q will be false because both are false. P or Q will be false because both are false. P then Q will be true because it's true only, or it's false only when P is true and Q is false. And finally, P if and only if Q is true because P and Q have the same truth values. Okay, so basically that's what I mean by truth value assignment. As I say here, each row, right, represents an assignment of truth values to the atoms. Okay, if there are two atoms, A and B, then you can verify that there will be four possible assignments of truth values to the atoms, right? A case where A and B are both true, when A and B are both false, two cases when A and B differ in truth values. Thus, the statement not A or B has four rows. So, on slide number 3, I have what I've done is I've diagrammed for you a truth table for 3 sentences: not A or B, A then B, and not A and not B. Okay, so if you look at the truth table, when both A and B are true, not A or B is true because B is true. A then B is true because both A and B are true. Now you have not parentheses A and not B. Now be careful about negation, right? The scope of the negation operator is determined by parentheses. If you just have a negation in front of a simple atomic sentence, then that is the scope of the negation. But if you have a parentheses and a negation outside, then the scope of that negation is whatever is in those parentheses. So for the last statement, the scope of the negation operator is A and not B. And we see that when A and B are both true, right, that makes A and not B false. And that makes, therefore, and when you negate it, it makes it true. When A and B are, when A is true and B is false, then that means A and not B are both true, and therefore A and not B is true, and the negation of true is false. When A is false and B is true, then what you have there is that A is false and B is false, and so A and not B is false. But if you negate that, then the whole thing is true. And finally, in the last row, if A and B are both false, that means A is false, even though not B is true. But false and true for conjunction gives you false. But then if you negate false, you get true. So you get true, false, true, true. Now, what you will notice is that these 3 sentences or propositions of propositional logic all have the same truth tables, right? Not A or B is true, false, true, true. A then B is true, false, true, true. Not parentheses A and not B parentheses is true, false, true, true. So when we say that these sentences all mean the same thing, and we call that logically equivalent. So 2 statements in propositional logic are logically equivalent if they have exactly the same truth values in all of the same rows. Okay, so what I want to do with you now is to show you how to construct a truth table for a complex sentence. And that's what I want you to do on the non-graded assignment that you'll be going over with your GA in this Thursday's labs. And then you will be expected to know this material for the final exam. I will give you some sentences on the final exam and have you construct truth tables for them. And what I'm showing you in today's lecture is how to construct those truth tables. So suppose we want to construct the truth table for the sentence A or parentheses B and C. Now remember from last week, the or is the main connective, and then the parentheses B and C, so A is a subsidiary connective. So the overall sentence is a disjunction. It's a disjunction of one atomic sentence with a conjunctive statement, right? So because we have 3 atoms, as I say here, our truth table will have, remember, 2 to the n, 2 to the 3 equals 8 rows, right? So there'll be a row when they're all true, a row when they're all false, and then the other 6 rows will be when they vary in truth value between one another. So there are altogether 8 possible truth value assignments for this sentence. Okay, rather than, you can kind of figure it out in your head, especially if there are only 8 rows, there's a more systematic way to determine these assignments for each column for A, B, and C. For the A column, we have 4 truths alternating with 4 falses. In the B column, we have 2 truths alternating with 2 falses. And finally, in the C column, we have 1 true alternating with 1 false, so that A, B, and C columns are as follows on the next slide. Okay, so notice here then that we have 4 and 4 for A, right? We have 2 and 2 for B, and we have 1 and 1 for C. And you can verify for yourselves that this is all 8 possible truth value assignments, all 8 possibilities for assigning truth values to A, B, and C. Okay, so you can verify this on your own. So again, the first column will have, I guess you could say, basically, it will have 4 and 4. All right. So that will be, I guess, what? Divided by 2. All right. So it'll be the variable divided by 2. So 4 and 4. So 8 values altogether divided by 2 gives you 4 and 4. The second column, B, there are 8 values, but now it's going to be divided by 4. So there'll be 2 and 2. And then C, there are 8 values, right? Eight values altogether. And we divide that by 8 and we get 1 and 1. So again, the first column for A will be 4 truths alternating with 4 falses. The second column for B will be 2 truths alternating with 2 falses. And the third column for C will be 1 true alternating with 1 false. And this gives you all 8 possible truth value assignments. And now you can then add a column and start calculating the truth values of the overall sentence that we're assessing, okay? All right. So what if we're, okay, so I didn't, you know what I didn't do? Oh, I'm sorry, I skipped one. My apologies here. Sorry, let's go back to, yeah. Okay, so sorry about that. I skipped one. There we go. That's the one I wanted to get to. So now remember we said that we were evaluating the sentence A wedge parentheses B and C. So what I'm doing here is I'm showing you how to calculate the truth values of the overall statement using the components and the basic truth tables for tilde, and, or, if then, and if and only if. So first of all, we know that one of the components A is 4 truths with 4 falses, right? We know that. We know that the B is 2 truths alternating with 2 falses, and C is true, false, true, false. So if you look at the first row, then B and C, true, true gives you true. Second row, true, false gives you false, because remember for and that the sentence is true only when both components are true. For the next row, false, true gives you false. For the next row, false, false gives you false. Then we go to the fifth row, and B and C are both true again. So true, true gives you true. But then in the other rows, at least one of them or both of them is false, so you get false, 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 all right? So that's how you get the truth values for B and C. It's true, false, 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 true, false, false, false. Then what we do is we compare it to A, which is 4 truths and 4 falses, using the connective or wedge. And remember that going back to the basic truth tables, P or Q is false only when both are false. So if we look here then, we see that A and B and C in the first row are both true, and so that gives us true for or. We see that A and is true, and B and C is false, but because one of them is true, that still makes the or true. We go to the third row. A is true, B and C is false, But again, you just need one to be true for OR to be true. And so A or B and C is true. We go to the fourth row. A is again true. Even though B and C is false, true and false for OR gives you true. Then we go to the fifth row. A is false, but B and C happens to be true, right? And so false and true for OR gives you true. But notice that for the last three rows, this statement is false because both A is false and B and C is false. So false or false gives you false. So we have 5 trues alternating with 5 falses. Okay. All right. So we say then that if you have a mixture of truths and false for the truth table for the sentence, we call that contingent. All right. So as I say here, notice then that the truth table for A, wedge B, and C has a mixture of truths and falses in the column for the main connective. A sentence of propositional logic, PL, that has a mixture of truths and falses is said to be contingent. Thus, a sentence not A or B is contingent. A sentence of PL that has only truths in the column, we say to be tautologous, right? And an example of a simple tautology is A, wedge not A or not A. That is sometimes known as the law of the excluded middle, and it goes all the way back to Aristotle in his works on logic. Another example is not parentheses A and not A. That means that A and not A can't both obtain. That's called by Aristotle the law of non-contradiction. Those are both tautologies. If you do a truth table, they will be true in all rows. So anyway, that's just a little, so if you're doing these sentences, let's say on the exam, I give you, or on the non-graded assignment, I give you a sentence of PL to assess using truth tables. What you're going to do is you're going to use the basic truth tables and you look where the parentheses are. The parentheses determine the scope of the main operator. And so you work within the parentheses and then you eventually determine the truth value of the entire statement. So here's a famous tautology in propositional logic. It's called the paradox of material implication. Basically, the paradox of material implication says that a false proposition implies any proposition. So if A is false, then A implies B, right? If A is false, then A implies B. That is called a paradox of material implication. So let's look at the truth table for that sentence. So again, because there are only 2 atomic components, A and B, we have a 2 to the n or 2 to the 2 or 4-row truth table. And systematically, the first column will be 2 truths alternating with 2 falses. In other words, the variable divided by 2. In the next row will be the variable divided by 4, true, false, true, false. And so this then exhausts all possible truth value assignments to A and B. There'll be a case when A and B are both true, a case when A is true and B is false, a case when A is false and B is true, and a case where both A and B are both false. So now we look at the overall sentence. So in propositional logic, it's kind of like doing elementary arithmetic. If I do 2 plus parentheses 3 and 4, then what I do is I calculate within the parentheses first. So 2 plus parentheses 3 and 4 will be 2 and 7, right? And then 2 and 7 equals 9. And you do the same thing in propositional logic. You do the calculations within the parentheses first. So if you look at A then B then, we know from the simple truth table for A then B that when A and B are both true, A then B is true. When A is true and B is false, A then B is false. When A is false and B is true, then that makes A then B true. And when both are false, that's going to again make A then B true. So remember that for an if then, the only time when it's false is when A is false and A is true and B is false. So we have true, false, true, true. Now we're told, we know that A is true, true, false, false, but if you negate A, then you'll get false, false, true, true. So now what we do is we compare not A with A then B and see what its truth value is for each row of the truth table. So in row number 1, A is false, not A is false because A is true. A then B is true, and so false implies true for the table for P then Q gives us true. We go to the second row. Okay, A is false, not A is false because A is true. A then B is false. False implies false in propositional logic for if then gives us true, right? Go back to the basic truth table, right? Okay. Then for row number 3, A is false, which makes not A true. A is false and B is true. So false implies true gives me true. So true implies true gives me true. And the final row. A is false, so that makes not A true. A then B, false then false gives me true. So true implies true gives me true, right? So what I'm using here is the basic truth table going way back to the first slide for A then B, right? Then remember, when both are true, P then Q is true. When P is true and Q is false, P then Q is false. Otherwise, P then Q is true. So that's what I was using to calculate the truth value of the overall sentence on this slide here. So because then not A then A then B have true in all rows, then we call this sentence a tautology. All right. Now suppose we negate this tautology. Well, as you know, if I have P and P is true, then not P is false, right? Notice here then that not A then B is true in all rows. So if I negate that, it's going to be false in all rows, right? And so a sentence that is false in all rows is said to be contradictory. Okay. So what we get then, if we negate that, is we get all falses in the column for the main connective. Any propositional logic that is false in all rows of its truth table is said to be contradictory. So if we negate our tautology, not A then B, then we obtain not A then B. And if you did the truth table for that, you would find that you get false in all rows. Okay, so therefore, there are altogether 3 kinds of sentences in propositional logic. There are tautologies, where the sentence is true in all rows of its truth table. There are contingent sentences that have a mixture of truths and false in its truth table. And you have contradictory sentences that are false in all rows of their characteristic truth table. Okay, so you can use then the truth table technique to determine the status of a sentence of propositional logic. You can use the truth table to tell whether it's contradictory, contingent, or tautologous. Now, what happens? So we know that if you negate a tautology, you get a contradiction. And of course, if you negate a contradiction, you're going to get a tautology. If you negate a sentence that's true in all rows, then it's going to be contradictory. If you negate a sentence that is false in all rows, then it's going to be tautologous. What about if you have a contingent sentence? Well, if you negate a contingent sentence, you'll get another contingent sentence. So remember the sentence that we evaluated a few slides back, A or B and C. We saw that it was false in the last 3 rows and true in the first 5 rows, so we called it contingent, right? Well, if you negate the whole sentence, like I have in the final column, not brackets, A or parentheses B and C parentheses bracket, if I negate the whole darn thing, then it's just going to change. I'm going to get the opposite truth values that I had with the original sentence. So with the original sentence, I had 5 truths and 3 falses. With the negated sentence, it just reverses, right? I have altogether 5 falses and 3 truths. But both sentences are contingent because you have a mixture of true and falses, right? So therefore, long story short, the negation of a contingent sentence gives you another contingent sentence. Okay, so hopefully you're all with me at this point. So again, the basic truth tables for tilde, it's false when P is true, and it's true when P is false. For P and Q, it's true only when both P and Q are true. For P or Q, it's false only when both are false. For P then Q, it's true only when only when P is true and Q is false. And for P, if and only if Q, it's true when P, Q agree in truth values and it's false otherwise. All right. Using those basic truth tables, we can then determine the truth value status of a complex sentence of propositional logic right? And remember that it's kind of like with arithmetic, you always work within the parentheses, right? So again, I gave you the example, 2 plus parentheses 3 and 4, that would be 2 plus 7. 2 plus 7 equals 9. And you do the same thing when you're calculating truth values for each row of a truth table in propositional logic. We saw also that the length of the truth table, the number of rows that you have, will be determined by the number of atomic sentences you have in the expression. If you have 2 atomic sentences, you're only going to have 4 rows, 2 to the 2 or 4 rows. So here for practice together, let's work on these 3 sentences to determine their truth value status. So notice, so the first sentence is A, then parentheses, B, then A. The second sentence is the same as the first sentence, except you put brackets around it and you negate it. The next sentence on the bottom is A, then B, implies parentheses, not B, then not A. Okay, so notice that all 3 sentences only have altogether 2 atomic letters, right? So each sentence then will have a 4-row truth table. So let's work out the truth table for each of these sentences. If we go to the next slide, we see that the truth table for A, then B, then A is as follows. Remember that there are 4 rows, and so there are 4 possible truth value assignments to A and B. There's a case when both are true. There's a case when they vary in truth value, and there's a case where when they're both false. Systematically, A has basically n divided by 2. So n is 4, so 4 divided by 2 is 2 and 2. The second column has n divided by 4, right? So that will be then 4 divided by 4 is 1 and 1. So 2 truths, 2 falses for A, 1 true, 1 false, 1 true, 1 false for B. Okay, now what I want to do is to calculate A, then B, then A. So let's then first of all calculate B, then A, which is a component. And that gives us B is true and A is true. So B, then A is true. B is false and A is true. So B, then A is true. Because remember, for the if then, false implies true still gives you true. A is false and B is true. B, then A gives us false, because true implies false for the if then always gives us false. And lastly, B is false and A is false. False implies true. And so therefore for B, then A, we get true, true, false, false. Okay. So now we're in a position to calculate the truth value of the overall sentence, A, then parentheses, B, then A, right? So I know that A is true and B, then A is true. True implies true, gives me true. I know that A is true and B, then A is true. True implies true, gives me true. I know that A is false and B, then A is false. False implies false, gives me true. Again, I'm referring to the truth table for P, then Q. A is false and B, then A is true. False implies true for if then gives me true. So notice then that this sentence is true in all rows. And therefore we say that the whole sentence then is a tautology. All right. Now, I didn't work out the truth table for the negation because we already know that A, then B, then A is true in all rows. If we put everything in brackets and negate the whole darn thing, then it's going to be false in all rows, right? So then not A, then B, then A will be false, 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 false. It's contradictory. So here's an example then of a tautologous sentence, A, then B, then A. It's true in all rows. Here's a sentence, or here's an example of a contradictory sentence. It's false in all rows because the sentence that it negates is true in all rows. Okay, a slightly more complicated sentence, A, then B, then not B, then not A. Okay, so if we look at this sentence here, it has 2 major components, A, then B, and not B, then not A. And of course, A, then B has the components, the atomic components A, B. Not B, then not A has the components not B, not A. And okay, so let's figure out the truth values of both sentences then independently, and then figure out the truth value of the entire sentence. So in other words, what we're doing is just like in arithmetic, you work within the parentheses first, right? So if I have 2 plus 3 parentheses plus 3 plus 4, then I work within the parentheses, right? So 5 and 7 gives me 12. So here, as before, I have two atomic components A and B. So altogether, then I will have 2 to the 2 or 4 possible truth value assignments to the atomic components. The first column will be n divided by 2. So the first column will simply be um, 4 divided by 2, which is 2 and 2. And then the last one will be n divided by 4, which is 4 divided by 4, which gives me 1 true, 1 false, right? Okay, so let's look at the first row. A and B are both true. You know that that will make A then B true as well, right? From the truth table for if then. If not, if B is true and A is true, then not B will be false and not A will be false. Well, for if then, false implies false gives me what? Gives me true, right? And so not B then not A is also true. And so therefore A then B is true, not B then not A is true. So true implies true gives me true for the first row, okay? Let's look at A and B in the second row. A is true and B is false. Well, we know by the truth table for if then that if P is true and Q is false, that makes P then Q false. So A then B is false in row 2. Now, what about not B then not A? Well, not B will be true and not A will be false. So true implies false gives me once again false. False implies false for the components gives me true. So A then B is false, not B then not A is false. False implies false gives me true. So in the second row, it is true. For the third row, A is false and B is true. So then A then B will be true, sorry, because A is false and B is true. For if then, that will make it true. Not B then not A. Well, not B is false and not A is true. False implies true once again gives us true. Okay, well, since both are true, then that's going to make the whole thing true. A then B, then not B, then not A true. So it's looking like it's going to be tautologous. We have to now look at the last row. A and B are both false. We know by the truth table for P then Q that will make A then B true. We know by the truth table for P then Q that not B then not A will also be true, right? Not B is true, not A is true. True implies true gives me true. So then A then B is true and not B then not A is true. So true implies true gives me true for row number 4. So as it turns out, this sentence is true in all 4 rows. And so we say that it is a tautology. So far, so good. Okay. All right. So anyway, long story short, a sentence of PL can have 3 statuses. Contingent, mixture of true and falses in its rows. Contradictory, false in all rows, tautologous, true in all rows. All right. So we've just gone over several examples. And so on the in-class assignment, the non-graded assignment on Thursday with your GA, I want you to do the same thing. Calculate for me the values of the sentences that I gave you on the assignment, and then tell me whether they're contradictory, tautologous, or contingent. Okay? We can also use truth tables to determine whether an argument is valid, right? So all that an argument is premise or premises and conclusion. And if I have an ordinary language argument, I can translate all the component sentences into propositional logic and then assess the overall argument. So as I say here, to construct a truth table for an argument, the number of rows is determined by, again, like with sentences, how many atoms are contained in the premises and conclusion combined. So the columns for the atoms are configured in the same way that they are for evaluating single sentences. Consider the following propositional logic argument. Premise, A then B. Premise, A. Conclusion, B. I'm sure you recognize this as an instance of the valid argument form modus ponens. So what's going to happen is that when we do the truth table for this argument, it's going to tell us that the argument is in fact valid. Now, in terms of truth tables, an argument is valid in propositional logic just in case there is no rule of the truth table where the premises are all true and the conclusion is false. If there is no such rule, then the argument is valid. If there is such a rule, then we say that the argument is invalid. So let's, in fact, use a truth table to determine the status of the argument. So here I have, actually, all that this is just the diagram for A then B, right? So the premise is A then B, and the other premise is A, right? And the conclusion is B. So I look at row 1. Both premises are true, but the conclusion is true. So that's not a case where the premises are true and the conclusion is false. The second row, one of the premises is true, but one of the premises is false. So that's not the case where both premises are true and the conclusion is false, and therefore that isn't a case where it's invalid. If we look at the third row, A then B, the premise A is false. And even though A then B is true, because one of the premises is false, and that's not a row where the premises are both true and the conclusion is false. And finally, in the last row, A is false. A then B is true. Okay? Well, again, that doesn't matter because this is not a row where both premises are true and the conclusion is false. So therefore, we say that the argument is valid. All right. So again, I have the definition of validity here in italices. A PL argument is valid if and only if there is no row of its truth table where the premises are all true and the conclusion is false. All right. So we can see then that this particular instance of modus ponens is, as we suspected, formally valid because there's no row of the truth table where the premises are true and the conclusion is false. Okay. Now let's look at a slightly more. By the way, remember affirming the consequent? We said that that's a variation of modus ponens, but it's invalid. So affirming the consequent is A then B, B therefore A. So again, using the same truth table, this time B and A then B are premises, and A is a conclusion. So we can see for the first two rows that the argument isn't invalid because the conclusion is true. And so it's not a case where the premises are true and the conclusion is false. Now, in the third row, the conclusion is false. If the premises are true and the conclusion is false, that would make the argument invalid. Well, B is true, right? And A then B is true because false implies true by if then gives us true. So here, row number 3 is a row where the premises are both true and the conclusion is false. Therefore, we say that this is an invalid argument. Now let's consider an instance of hypothetical syllogism. Again, we know that hypothetical syllogism, any instance of that argument form will be valid. There will be no row where the premises are true and the conclusion is false. So consider the premises, A then B and B then C. So, and then the conclusion is A then C. So if we look at the argument, altogether, there are 1, 2, 3 atomic variables, right? So then the truth table for the whole argument will be 2 to the third or 8 rows long. So this then is the truth table for A then B, B then C, A then C. All right. Now, since there are 3 variables, it's going to be a little more complicated, right? And we want to make sure that we exhaust all 8 possibilities. So to do that systematically, for the first column A, it's going to be n divided by 2. So it'll be 8 divided by 2, which is 4 truths, followed by 4 falses. In the second column, it will be n, which is then it will be altogether it will be 8. It will be so for that column, for the first column, then again, it's 4 and 4. For the second column, it's going to be 2 and 2, right? True, true, false, false, true, true, false, false. Okay. So in this case, it will be altogether. So it will be an 8-row truth table. So 8 divided by 2 will give us 4. Okay. And in the last column, it will be 8 divided by 8, 1 and 1. So again, 4 truths alternating with 4 falses. B is 2 truths alternating with 2 falses. And then we get true, false in the last column. So as you can see intuitively, we've exhausted all possible truth value assignments to the components A, B, and C. There's a case where A, B, and C are all true. There's a case when when A and B are true, but C is false, a case where A, C are true and B is false, a case where A is true and the other two are false, a case when A is false and the other two are true, a case where A and C are false, but B is true, a case where A and B are false and C is true, and a case where all three are false. And to get that systematically, again, so it's an 8-row table. So the first column will be 8 divided by 2 equals 4, right? That is altogether 2 to the n divided by 2 gives you 4. The second column is 2 to the n divided by 4, right? Will then give you 2 and 2, all right? And 2 to the n divided by 8 divided by 8 will give you then 1 and 1. Right? Okay. So again, for the first one, 2 to the n divided by 2, 2 to the n divided by 4, and the last one is 2 to the n divided by 8. Okay. So we've got all of our truth value assignments. Now what we have to do is determine the truth values of the two premises and the conclusion. What we're looking for in this argument is whether there is a row of the truth table where the premises are all true and the conclusion is false. Now, again, in this argument, there are two premises, A then B and B then C, okay? So what we're going to look at are the rows where A then C is false and where these two are true. So if we look at the first row, pardon me, we see that A then B is true. True implies true gives you true. We see that B then C is true because true implies true gives you true. And A then C is true because A is true, C is true, true implies true gives you true. So here you have two, the premises are both true, but then the conclusion is true. So this is not a case where the premises are true and the conclusion is false. You go now to the second row. The first premise is true because true implies true gives you true. The second premise is false because true implies false gives you false, right? Then right away we know that this is not a row where the premises are both true and the conclusion is false, so we discount the second row. Then we go to the third row. True implies false gives me false, so we don't have to worry about the third row because that's not going to be a row where the premises are both true and the conclusion is false. Now we go to the fourth row. Okay, true implies false gives me false. Again, we can discount that row because that's not going to be a row where the premises are both true and the conclusion is false. So as of the first 4 rows, we have no indication that the argument is invalid. It seems to be okay. So let's look at the last 4 rows. Okay, row number 1, premise 1 is true, or row number 5 rather, premise 1 is true. False implies true gives me true. Premise 2 is true. True implies true gives me true. However, A then C is also true because false implies true gives me true. So that is not, so even though both premises are true, it is not a row where both premises are true and the conclusion is false. Now we go to the 6th row. False implies false gives me, that should be actually, sorry, false implies true gives me true. So anyway, that's gives me true. Sorry, no, that's right. Yeah, so that's true. Okay, actually that's a typo. The B should be true there. My apologies. B then C. Okay, true implies false gives me false. So this row can be discounted because it is not a row where the premises are both true and the conclusion is false because the second premise is false. Now we go to the 7th row. Okay, false implies true gives me true. False implies true gives me true. So both premises are true. However, A then C is also true because false implies true gives me true. So this is not a row where the premises are both true and the conclusion is false. Last row to consider. All three A, B, and C are false. Okay, so that makes A then B. False implies false makes it true. False implies false makes it true for B then C. False implies false makes it true for A then C. So even though both premises are true, there is no case where the premises are true and the conclusion is false. And so overall then, this argument is said to be valid. All right. In any row where the premises are true, namely rows 1, 2, 7, and 8, in all those rows, the premises are true, but then the conclusion is also true. So therefore, the argument is formally valid. Okay, it's up to you if you want it. You don't have to use a shortcut. That's just kind of an aside. Okay, for practice, determine whether the following propositional logic arguments are valid using the truth table technique. So what I've done is I've given you the following argument: A wedge parentheses B then C, tilde parentheses tilde B or C, and the conclusion is A. So if you look at that argument, they're all together going to be, there are 3 atomic sentences, and so there are going to be 2 to the 3 or 8 rows of the characteristic truth table. And so what I do on the next slide is I outline the truth table. Okay, so there's the truth table. As before, we have 3 atomic variables, so we will there have 2 to the 3 or 8 rows. We'll have 2 to the 3 divided by 2 trues for A, alternating with 2 to the 2 divided by 2 falses, right? So 4 trues and 4 falses. For B, 2 trues, 2 falses. C, 1 false, 1 true. And we see that if you verify, those represent all possible truth value assignments to the atomic variables. Okay, so what I do then is I have additional columns, a column for each of the premises and a column for the conclusion. Really for A, that's easy because I just rewrite the column for A. So A is true, 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 false, 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 false. Okay, now notice that I can immediately discount the first 4 rows because those are not rows where the conclusion is false. So it's true, 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 true. And so therefore, those first 4 rows are not cases where the premises are both true and the conclusion false, because the conclusion in all those first 4 rows is true. So we really only have to consider the last 4 rows. Only in the last 4 rows is A, the conclusion, false. All right, that's really the only row that we need to consider. Well, let's look at those last 4 rows. A is false in the 5th row, but notice that not B or C is false. And so that is not a row where the premises are both true and the conclusion is false. If you look at row number 6, we see that if you look at number 6, we see that A or B then C is false, right? And so then again, this is not a row where the premises are both true and the conclusion is false. We look at the last row, or sorry, no, the second last row. One of the premises is false, namely not B or not C. Therefore, that is not a row where the premises are both false and or true and the conclusion is false. And lastly, in the last row, not parentheses, not B or C parentheses is false. So that is not a row, right? That is not a row where the premises are both true and the conclusion false. So therefore, in conclusion, there is no rule of this truth table for this argument where the premises are all true and the conclusion is false, and therefore we say that this argument is valid. Okay, so this lecture then tells you how to construct truth tables for both sentences and arguments of propositional logic. And what I did on the non-graded assignment that you will do this Thursday in lab is I gave you a number of statements and arguments. What I want you to do is to assess them using truth tables. All right. On the exam, what I'll do is I'll give you sentences in English. You translate them to propositional logic, or I'll give you arguments in English, translate them to propositional logic. Then you do truth tables to see whether the sentences are contingent, contradictory, or tautologous, and you do truth tables to see whether or not the argument is valid or invalid. If you have followed both online lectures, you'll have absolutely no problem doing the final exam. Okay? All right, so this is the last lecture then for the semester. Good luck on the final exam and good luck with all of your exams this semester.